Hi everyone, Ross Satchell from Microchip back again. In the previous video in this series, I introduced the concept of bare metal or register level programming, showed you how to access the datasheet through MPLAB X, and showed you the tech brief TB3262 getting started with writing C code for AVR MCUs, and also some of the nomenclature associated with using the device header files. In this video, we will cover more of TB3262, where we will create a new bare metal project and main.c file, find the device header file and its macros, and also learn how to use bit masks, and group configuration masks. So let's dive right in. As we did in the previous video, open MPLAB X and connect your attiny 1627 Curiosity Nano, ensuring the kit window appears. If it doesn't appear, please refer to the first video in this series on how to fix that before moving forward. Now let's create a new project. Click File, New Project. A pop-up window appears with Microchip Embedded and Standalone Project already selected. Click Next. Now in the Device field, type 1627 and select the attiny 1627 from the drop-down list. Then in the Tool field, select the attiny 1627 Curiosity Nano from the list, then click Next. Now select XC8 as your compiler and click Next. Now give your project a name. I'm calling mine Tiny2 Bare Metal 2, then click Finish. That will then create an empty project for us. If we look under the header and source files, we can see that they are empty and that the only file set up for us is our make file. So let's set up a main.c file. Right-click on Source Files, then select New, then main.c. In the pop-up window, it gives the default name of new main.c, but I like to call mine main.c. Then click Finish. That then creates an outline of a main.c file. The first thing we should do before starting to write any code is to build the project. This is so that if there are any problems, we can easily determine whether it's a problem with the project itself or our code that's causing the problems. So click on the Clean and Build Main Project button on the toolbar, and then we can see the green Build Successful message in the output window in the lower part of the screen. Now before we start writing code, we need to figure out what we're going to do. So let's open both the datasheet and TB3262, link in the description below, in your PDF reader of choice. We will pick up from where we left off in TB3262, which was section 2. We had covered the part about the dedicated header file being included by default when we defined our device while initially setting up the project, and we can see the header AVR/IO.H being included. You may recall from the first video in this series, I touched on how registers are simply locations in memory. In section 2.1, it explains that all registers for a given peripheral are placed in a continuous memory block, which makes it possible to arrange all peripheral modules using C structures, also known as structs. Then section 2.2 covers module structures, and we have two examples, being the ADC struct and the port struct. Since we will be using the port struct to set up the clock soon, let's focus on that one for now. So we can see some of the parts of the port struct are the data direction register, as well as the data direction set and clear registers. There's also output value, as well as set and clear, interrupt flags, and individual pin control. Now on to section 2.3, which is all about masks. Masks are used to isolate our bit or bits of interest in a register. We can use bit masks manually to set or clear a bit or group of bits, or to read a bit or group of bits. So for example, if I had an 8-bit register that held the binary value 11010011 and I wanted to read bit 3, I could bitwise OR that register with a 1 left bit shift 3, and then the code would look like this. But the problem there is that it's not always clear what the user is trying to do, and it can be more difficult to debug as it requires very careful perusal of the datasheet while coding and debugging to prevent and find errors. The solution to this is using masks defined by macros, which result in code that is much more human readable. To find these macros, we can follow the header xc.h by using Control-click on the header file name. Then in xc.h header file, we can see that AVR/io.h is included here. So let's follow that one using Control-click again. Now in the AVR/io.h header file, we can see the device definitions and their associated header files. If we search using Control-F and enter 1627, since we're using an AT Tiny 1627, we get no results. So where is the header file? If we scroll to the bottom, there after the last device header definition is this following code. So let's go through it. First we have, if the AVR device library name is defined, then we have this inline function definition. It defines concat, which is short for concatenation, of A and B. Then we have A ##B. This ### operator is known as the token pasting operator, which is part of the preprocessor. When the macro is expanded, the two tokens on either side of the token pasting operator are combined into a single token. That single token then replaces the token pasting operator and the two tokens in the original macro. Then the next line defines header 1 with A/B parameters as the concatenation of A and B. Now the third line defines the AVR device header as AVR/, then the concatenation of IO and the AVR device library name. So basically, these three defines build up a string that will be the device header file include. For the AT Tiny 1627, the AVR device library name is TN1627. So then the generated include becomes AVR/IOTN1627. And we can manually type that in at the top of our main.c file and then Control-click to follow it to see all of the macros. If we then do Control-F to find and then type in clock control, we can see the struct used for that module. Then looking at just a few of the entries, we have main clock control A and B, and we have the 20 MHz oscillator, the 32 kHz oscillator, then onto the enumerations or enums. And we can see we have clock select enum entries that end in _GC. Let's jump back to TB3262 to see what that's all about. Picking up where we left off was section 2.3. Let's look at the different type of masks available to us. It states that bit masks are used when setting or clearing individual bits, while bit group masks are mainly used when clearing multiple bits in a bit field. Table 2-1 shows the Control D register of the ADC0 module. We have the bit position ranging from 0 to 7, the mask required to isolate each bit, then the name of each bit, and then the bit field name. Bit fields are names given to bits grouped together, and we have two there, the initialization delay bit field and the sample delay bit field. There's an important note below. Since the bit names need to be unique for the compiler to handle them, all bits are prefixed with the module type they belong to. Then they give the example of bit definitions belonging to timer counter A being prefixed with TCA_. So that makes sense, as we saw in the device header file, the clock control bit definitions were starting with clock control _. Next in the tech brief, it talks about differentiating between bit masks and bit positions using a suffix, with bit masks having the suffix _BM and bit positions having the suffix _BP. Then there is also group positions, which is the bit position where a group configuration begins in a register. Then in figure 2-1, it gives an example for the ADC initialization delay bit mask having the module name, then the bit name, then the bit mask suffix. Now on to group masks, which are used to set or clear the relevant bits in a bit field. The naming convention is similar to that of bit masks, except for group masks, this suffix is _GM. There is an example of clearing the bits in a bit mask by bitwise inverting and then bitwise ANDing a group mask to clear the bits in a bit field. Then we have group configuration masks and enumerators. So rather than the user manually clearing a bit field and then setting the relevant bits for a configuration, the user can instead use a group configuration. These have the suffix _GC and use names that greatly increase the human readability of setting up bit fields, while minimizing the possibility of setting bits in a bit field incorrectly. Figure 2-3 has the example of setting up the ADC module prescaler in the peripheral clock to divide by 4. Using group configurations make writing and maintaining code very easy, as it is very clear what configuration the mask selects. Then table 2-2 really drives this home, as we can see that to clear and then set a prescaler using bit masks introduces the possibility of making simple mistakes which can be troublesome to find and correct, while using the group configuration masks does the work for us and it makes it very clear what setting is being configured. Finally, we have enums, which use a similar naming convention but end in _enum and contain the group configurations for a given module. With all of that in mind, join me in the next video where we will set up an I/O pin as an output and toggle the onboard LED every 1 second.